Hello, everyone. It's my honor to present a simple introduction on our hierarchical supervision and shuffle data augmentation for 3D semi-supervised object detection. State-of-the-art 3D object detectors are usually trained on large-scale datasets with high-quality 3D annotations. However, such 3D annotations are often expensive and time-consuming, which may not be practical for real applications. As shown in the left figure, a natural remedy is to adopt semi-supervised learning by leveraging a limited amount of labeled samples and abundant unlabeled samples. Current pseudo-labeling-based SSL object detection methods mainly adopt a teacher-student framework, with a single fixed threshold strategy to generate supervision signals, which inevitably brings confused supervision when guiding the student network training. Besides, the data augmentation of the point cloud in the typical teacher-student framework is too weak, and only contains basic downsampling and flip and shift, which hinders the effective learning of feature information. Hence, we address these issues by introducing a novel approach of hierarchical supervision and shuffle data augmentation, which is a simple yet effective teacher-student framework. As shown in the right figure, the teacher network generates more reasonable supervision for the student network by designing a dynamic dual threshold strategy. Besides, the shuffle data augmentation strategy is designed to strengthen the feature representation ability of the student network. Extensive experiments show that STA consistently outperforms the recent state-of-the-art methods on different data sets. The pipeline of our STA framework is illustrated in the figure, which is derived from the basic teacher-student mutual learning framework. In the burn-in stage of training, we train the detector in a fully supervised manner with the labeled scenes and keep the same setting as the used detector. Then, both the teacher network and student network are initialized with the same pre-trained weight parameters. In the mutual learning stage, there are 3 steps in each training epoch. The first step is to generate 3 kinds of dual thresholds for each class in a global view, as shown on the left of the pink dotted line in the figure. Specifically, we construct a confident scene set composed of labeled scenes and mined scenes, whilst its weak augmentation is sent to the teacher network for predictions. Then we sequentially input each scene and its weak augmentation into the teacher network to produce a pair of predictions. Based on those pairs of predictions and the object information, we design a dynamic dual threshold generation strategy to obtain 3 kinds of dual thresholds for each class in terms of confidence score, objectness score, and IOU consistency. The second step, see the right of the pink dotted line in figure, is mainly to mine the hierarchical pseudo-labels. Specifically, each unlabeled scene and its weak augmented scene are sequentially input to the teacher detector to produce a pair of predictions. Through 3 measure rules based on the dual thresholds obtained in the first step, we can generate the hierarchical supervision, high confidence level pseudo-labels, ambiguous level pseudo-labels, and low confidence level pseudo-labels. We add all high confidence pseudo-labels into the confidence scene set for the next dual threshold generation. We also add the ground truth from labeled scenes into the first group for following student network training. In the third step, we use the hierarchical supervision composed of 3 groups of pseudo-labels to train the student network with our designed shuffle data augmentation, and then update the teacher network by the EMA strategy. After the mutual training step, we use the 3D detector from the student network as our final detector. Through the above procedure, we can see that our design framework can train any off-the-shelf 3D detector which consists of a backbone and a detection head. We first evaluate our proposed model on the popular Kitty dataset. Table 1 lists the results of different methods. From this table, we can observe that our approach significantly outperforms the state-of-the-art methods. Specifically, our approach has a remarkable boost in the car class for all settings, which has improvements of 7.4, 5.3, and 4.6 points compared to the PVR-CNN baseline for 1%, 2%, and 20%, respectively. Even compared to the recently proposed DET match which uses 2 modalities of LiDAR and RGB, our methods just with LiDAR still have better results for most of the settings. For the more challenging Waymo dataset, our approach still has a significant improvement in performance compared to the state-of-the-art methods. As shown in Table 2, our approach surpasses debt match. It is worth mentioning that the proposed method achieves 29.1 map for cyclist, which far exceeds the baseline. To summarize, our contributions are as follows. We propose a novel hierarchical supervision generation and learning strategy for the teacher-student model. This strategy can provide the student network hierarchical supervision signal, which can fully utilize the output of the teacher network. We propose a shuffle data augmentation strategy that can strengthen the feature representation ability of the student network. Our proposed hierarchical supervision strategy and shuffle data augmentation strategy can be directly applied to the off-the-shelf 3D semi-supervised point cloud object detector, and extensive experiments demonstrate that our method has achieved state-of-the-art results. Thank you for your listening.